Section 1.1, Functions and Models. There are 4 objectives in this section. First is to determine if a table, graph, or equation defines a function. Secondly, to find the domain and range of functions. Third, to use function notation to evaluate a function. And then lastly, applying real-world information using a mathematical model. All right, let's begin by looking at a common example of a function. Sometimes we need to convert Fahrenheit to Celsius and Celsius to Fahrenheit temperatures. Suppose a child's normal temperature is 98.6 degrees Fahrenheit. The only thermometer available measures in Celsius. We take the child's temperature and we find that the temperature is 37 degrees Celsius. Does this reading indicate that the child's temperature is normal, or is this child running a fever? Well, we would use this function listed here to convert that Celsius temperature to Fahrenheit. This is a function to determine Fahrenheit temperature. It is a function of Celsius temperature, right? Well, let's see what that Fahrenheit temperature would be. It's going to be 9/5 times that temperature in Celsius, which is 37 degrees, and then plus 32. Okay, so we can pull up a calculator. It doesn't want to wake up. Let's quit out of that and find out what that is. So it's going to be 9 divided by 5, or 9/5. And I should put that in parentheses, probably, to indicate that I want that 9 divided by 5, and then I'm going to multiply it by 37. 9/5 times 37, and then we'll say plus 32. And we see that the Fahrenheit temperature is 98.6. So this particular child does not have a fever. This child has a normal temperature. Okay. All right, so let's take a look at the definition of a function. Function can be thought of as a rule or correspondence that assigns each element of an input set, we might call that the domain, to exactly one element of an output set. We usually call that the range. So conceptually, we think about it like this. Say we have a function, all right? Here it is. This is our function. All right, we're just going to call that function f, right? It's going to receive inputs from this set of elements called the domain. And it's going to do something. The function is going to do something when it gets an input, and it's going to produce outputs, and it's going to put them in a different set, and we call that set the range, right? So for example, we may have a function that says take an element and square it, right? Maybe we have a function, call it x squared. Take something from the domain, square it, put something in the range. Well, if we take a 2 out of the domain and we feed that into the function, when we square it, 2 squared, of course, is 4. And when it comes out, it'll put a 4 into the range. Okay? So we can present functions different ways. We can present functions as sets of ordered pairs, a table, a graph, an equation, or maybe even a verbal description. If we look at that same function up there, the squaring function, and we decide to define it as a set of ordered pairs, well, we might not know all the values, but we could define some of them. So a set of ordered pairs would look like this. Curly bracket indicates that's a set of something coming. And let's see, maybe that set of ordered pairs looks like this. The first ordered pair has an x coordinate or an x value of -2 and a y value of 4. Then we may see -1 and 1 in that set. 0, 0 would be another ordered pair. 1, 1, maybe 2, 4. Okay, there's a set of ordered pairs. We could present a function as a table of values, right? As a table, it might look like this. Let's see, let's make them columns. We'll have an x column, we'll have a y column. When x is -2, y is 4. When x is -1, y is 1, 0, 0, so on and so forth. Okay. We can present a function as a graph, right? As a graph, this function would look maybe something like this. Let's see. When we graph the x squared function, it's parabola, looks a little bit like that. We can present that function as an equation, or sometimes I call this the algebraic form, right? In the algebraic form, or as an equation, it would look like this. Y equals x squared, right? And then lastly, I mean, we might even say a verbal description. As a verbal description, we may say this function is defined as, let's see, we might say it's multiply the input by itself. Okay. So all different ways to present a function. All right, so here we have a function that is presented on the right-hand side as a table of values, right? From that table of values, we could indicate ordered pairs, right? So if we were doing ordered pairs, it'd be like this: -5, -7, -3, -2, so on and so forth, right? And if we plotted these ordered pairs on a graph, it would be the graph that we see over to the left. Now we just see some points on there. Sometimes we call that a scatter plot. We just see some points on there. We're not connecting the points because we don't know the rule, right? Or we don't know the equation or the algebraic representation of this function. We only know certain x's and certain y's, or certain inputs on the y that it corresponds to, all right? So we said that the inputs to a function, a lot of times those are referred to as the x value, or the x coordinate in an ordered pair. The inputs to that function are the set of possible inputs would be the domain, right? So that's why it's going to refer to the x's. So for this function here, the domain is just going to be the set of all those x's that we see, the x coordinates. So all of these blue points here have the coordinates listed over here to the right. The x's of all x coordinates of all those points are -5, -3, -1, 0, 3, and 5. Right? The range of a function is the set of all possible outputs of that function. A lot of times we refer to those as the y, right? So for this function here, the range is going to be the set of all those y coordinates, or -7, -2, 6. Now look, we have -7, -2, 6, and another -2. Do I have to repeat that in the set? No, I can skip over that. I do need to put that 5 in there, though. That's not there yet. But there's another -7. That's okay. I don't have to have that in there. All right. Now let's pause here for a minute. Let's go back and look at the definition for the function. The definition for the function had an interesting phrase in it. It said it's a ruler of correspondence, but look at this. This phrase here, this exactly one phrase, is very important. This tells us that whenever I pick some element of the domain, whatever it is, it's only going to correspond to only one element in the range, right? I like to think of functions as being trustworthy, right? If I pick an element from the domain, I apply the function to it, I can trust that function that the output that I'm going to get is only one value. There's not going to be more than one, right? So if I look at this function here, and I put it against that test, I want to determine, is this really a function? That would tell me that each x must correspond to only one y. Well, -5 corresponds to only -7. That's good. -3 is only -2. -1 is only 6. 0 is only -2. So does it matter that -3 also corresponds to -2 in the output? No, that's perfectly fine, as long as -3 only corresponds to 1y, right? So it's okay if 0 also corresponds to -2. 3 corresponds to 5, of course, and look at 5 the x value of 5 corresponds to a y value of -7. But there's only one y that we get from 5, so it's still okay. It doesn't matter that -5 also gives us -7. All right, so that we found the domain and the range from that function by listing out all the x coordinates, all the y coordinates. When we have a graph like these two here that are continuous, it's not possible to list out all the x's and all the y's. So instead, what we want to do is we want to identify the domain and the range as an interval. All right. On this first graph over here on the left, right, we can see that this graph has an arrow at the end here indicating it keeps on going all the way to -infinity, right? So if I wanted to find the domain and it's continuous, I would need to first specify the smallest value or the lower bound, and then specify the highest value or the upper bound, right? And we close those values in parentheses to say it's an interval. Well, let's see, what would the lowest value be? Well, since it goes to -infinity, I just want to say all the way to -infinity. Now the upper bound, the rightmost or the highest value in this domain is going to be 4. Right? So we want all the x coordinates of all the points on that graph specified as an interval for the domain, because domain refers to x. Now for the range, we want the y's, right? The range is the y. So here we want to look for the lowest point on this graph to the highest, all right? The lowest point looks like it's here with a y coordinate of 0, right? The coordinates of this point are 4, 0. So the y coordinate is 0. So it looks like the smallest point is 0. What's the highest point? Well, if it goes off, let's see how it's tilting upward here. If I continue it, it's going to the left forever and ever. It's also going up forever and ever. So the highest value in the range, or the utmost value here, we're going to have to say is going to be a positive infinity. Okay. Do one more example, this next graph over here on the right. What's the smallest x and the highest x? The smallest x looks like it's -3, right? Right, the smallest x is -3. The highest looks like it's +3, right? The comma in between these is telling me all the values in between -3 and +3, right? Now this one has this little closed dot at the end, right? So that means include the end value as well. So we put square brackets around that interval to tell us to include that end value as well. For the range, again, this is the y's. We want the lowest point on the graph to the highest. The lowest point is here, down here, and it has the coordinates of, we'll say -3. What is that? Maybe that's negative. We're going to estimate. We'll say that's -27, right? So the smallest part on my range is going to be -27. The highest point, or the largest y, this is up here. I don't know. Let's estimate that as 340. Okay, so the largest y then is going to be 40. Okay. Okay, so not every table of values is going to be a function, right? Not every set of ordered pairs is going to be a function. We already talked about that the input or the element in the domain has to correspond to only one element in the range, but also a function can be considered to have an independent variable and a dependent variable, right? The independent variable would be the input. The dependent variable would be the output. So what we're looking at here is some data, some old data about PC, personal computer usage, or PC. US sales of personal computers, that's going to be this S in this second column, right? And it's in millions of dollars, right? And it's being listed out by year, X, that's in our leftmost column. So could we say here that S, or sales, is a function of X, or the year? Is sales a function of the year? Okay, well, we have to ask ourselves one thing. For each year, is there only one sales value, sales number? From this data that I see here, it looks like yes. So then I could say that sales is a function of year. In other words, the sales amount, the dollar amount, depends on the year. So the answer to this question would be yes, sales is a function of year, because whatever the value of the sales is depends on the year that it's listed in. Okay, is it truly a function? Does each year have only one sales value? Yes, that looks fine. If I were to add one more row, though, I could make this not be a function. Say I added a row that said 2,000 for the year and 40.0 for sales. Kind of doesn't make sense, does it? But look, here it says in the year 2000 there was 46 million. But when I added this, it says also in the year 2000 we have 40 million. Well, that's not trustworthy. Right? It's not trustworthy, right? So then I have to say then that that is not a function. Oops. If after I add that last column. All right. Okay, here's two equations. With these two equations, look at the one on the left. Can I say that the equation on the left defines y as a function of x? Does the value of x determine what the value of y will be? Well, that's kind of weird, right? Look, the value of x determines what y squared is going to be. Look at this one over here. The second one, does the value of x determine what y is going to be? I like that second one better, to say y is a function of x, right? Because clearly y is some calculation. I could put a value for x in there like -1, right? Negative of 1 squared would be -1 plus 6 times -1. That'd be -1 minus 1. I could say that y was -7. Yeah, so that one looks more like that y is a function of x. This one, this is weird. I might be able to rearrange things algebraically to make it look like y is a function of x. Say if I maybe took the square root of both sides, the square root of y squared is just y. So then I could say y is the square root of 4x minus 4. That looks a little bit more like a function, doesn't it? I can find the value of y. If I put 1 in for x, right, 4 times 1, that's 4 minus 4 is 0. The square root of 0 is 0, right? So that lets me determine the value of y. Okay? When we graph a function, it's really easy to tell if it's actually a function or not. And that's if it passes the vertical line test. All right? The first graph on the left here is, in fact, a function, because look at this red vertical line. If I move this left to right across that graph, it does not intersect that graph in any more than one place. When it's here, it intersects it right there. If I move it somewhere else, it only intersects it once. Compare that to the graph on the right. That is not a function, because when I move that vertical line left to right across the graph, it intersects the graph in two places, lots of times, right? Oops, doesn't move in both that time. It does intersect only one place, right there, right? But there's too many times that it intersects in more than one place, so we would say it is not a function, right? So if we go back and look at these real quick and graph them, well, we could stick them in the graphing calculator and look at them that way. Let's go ahead and put them in. To enter the equation in the graphing calculator, we'll do the one on the right first. First, we hit this y equals key, and that can clear out what I have in there. That gives us a place. That gives us a place to enter the equation. So y then is going to equal negative, or the opposite of, that's this white key down here at the bottom. That's the opposite of key. And then we want x squared, so x, and then we'll hit x squared to square it, right? And then plus 6x. There's the x key up there. Can we enter that in? Let's just use a standard viewing window to see if that works for us. So I'll say zoom, zoom standard, which is option 6 down there. I can either arrow down to it or type a 6. And that'll just give me a 10 by 10 grid. That's a standard viewing window. It looks like that was fine for this particular equation. Is that actually a function when we look at the graph? Yeah, that passes the vertical line test. I cannot imagine a vertical line that would intersect that graph in more than one place, right? Let's put that other one in there after I took the square root of both sides so that I've got a y equal situation. All right, so y equals the square root of 4x minus 4. The square root key is there. I'll do second x squared. That gets me to square root. And then I'll just type in 4x minus 4. I got that one in there. And let's look at them both on the same graph. Why not? Hit the graph key. There's the first graph. Here comes the second graph. And I can see that the second graph is also a function. If I go ahead and remove that first one, so I can go over here and just press enter. I arrowed over, and if I press enter, I can make it a thick line graph or kind of a triangle graph or dots, or I can just make it a dotted line or take it right back to what it was originally. I'm just going to make it circle something different so we can differentiate it really well. Go back and look at that graph. See, I don't care about that first graph. I just made it. I showed the movement. Now, looking at the second graph, it's just going to be a line again, and we can see that does pass the vertical line test. All right. Look at this graph here. This is the function listed here, 2x cubed plus 5x squared minus 28x minus 15. This is the graph of that function. And whenever you don't see an open circle or a closed circle at the end, assume there's arrows. So if we want to use this graph to find the value of f of negative 2 and f of 4, what we're actually doing is evaluating this function f, and we're evaluating it when x is negative 2, right? So to do that, what I want to do is find where is x negative 2 on this graph. Okay, there's a negative 2. The point on the graph looks like it's about right there. I want to make it nice and thick and make it sort of fit better, right? The coordinates of that point are about negative 2. Oh, it's probably not on 40, so I'll probably have to say maybe 43. We'll estimate like that. All right. Now, what about f of 4? So negative f of negative 2 is 43. Computer's acting up here. Let's see. That's a 3. And then f of 4, right? F of 4 is what? Let's see. Where is 4 on the graph? It looks like it's about right there. Coordinates of that point are going to be 480. Okay, so it looks like f of 4 is 80. Right? Now that's kind of estimating because it's not real clear on the graph what's what. All right, but we can find more specifically what that value is if we just use the equation to evaluate f of negative 2 and f of 4, right? Using the equation to find f of negative 2, we're just going to substitute negative 2 in for x and simplify. So 2 times negative 2 cubed plus 5 times negative 2 squared minus 28 times negative 2 minus 15. And you can plug all that into the calculator, and you'll see that that actually equals 45. Okay, so our estimate here was close, but not exact. The equation gave us an exact answer. Right, what about f of 4? Same thing, plug 4 into that equation for x. So 2 times 4 cubed plus 5 times 4 squared minus 28 times 4 minus 15. Plug all that into the calculator and we get 81. So again, our estimate was close, but the equation gave us the exact value. All right. Let's look at an example with real-world data now. This graph shows us the number of elderly men in the workforce by certain years, right? For certain years. We've got some years between 1950 and 2050. All right, now looking at this graph, we want to find and interpret G of 2020. All right, so this function is being called G. It's a function of the year. We'll call the year T. So we'll say it's G of T is the value of the function by year. So T is our independent variable, right? Our input or our domain, right? G of T would be our output, our dependent variable or our range. So G of 2020, where is the year 2020 on the graph? There's 2020 on the graph. It looks like it's here. So we can easily say that G of 2020 equals 21. All right. Now with this same data, say we want to find which inputs, which independent variables, or which values of the domain T result in an output of 19.6 million, right? Or give us G of T equal to 19.6. Remember, our vertical is G of T and our horizontal is T. Well, we need to find where G of T is 19.6. Well, here we can see that G of T is 19.6 in the year 2030, right? So that's true. It's in the year 2030. But look, there's a few more that aren't exactly labeled. 19.6 is about here, right? If I draw a line over, try to do a nice line, but it won't be perfect. It's going to look something like that. So it looks like there's other years, right? This probably shouldn't cross right there. It crosses a little bit above that. So it looks like a little bit past the year 2010, right? Somewhere in that year 2010, probably. There's another occurrence in 19.6. And then also a little bit before 1980. I don't know when that is. I'm going to estimate that right there. I'm going to say that's at 1977. Okay. With the same data, what would be the maximum? What would be the maximum number of elderly men in the workforce? Well, the maximum is going to be the largest G of T that we see, right? So it looks like that's right up here, 45.8. Okay, let's do one more thing in this lecture. Let's see if we can use a function to answer some questions. Here we have a function that shows us public healthcare expenditures for the period 2010, the year 2010 through the year 2032. Okay, we have a model right here. E of T equals 738.1 times 1.065 raised to the T power. Okay, E of T is in billions of dollars, and T is the number of years, look at this, after 2010. So what value of T would represent the year 2020? Well, it's the number of years after 2010, so I would have to subtract 2010 from that 2020, and I see that a T equal 10, a T value of 10 would represent the number of years, would represent the year 2020. So if I want to approximate public healthcare expenditure for the year 2020, what I want to find is E of not 2020, but E of 10. All right, and that would be 738.1 times 1.065 raised to the 10th power. All right, when I put all that in my calculator, I end up with $1,385.5 billion. The dollar symbol up there to show what our units are. Okay. The last part in this question here says, use this model to estimate the public healthcare expenditures for the year 2025. 2025. So that's in the future. This is, if the model's good, this might be a good way to predict things, right? Well, let's see. The year 2025 is going to be how many years after 2010? Looks like 15 years, right? If I subtract out that 2010. So what I want here is a t of 15. So I want to find e of 15. Okay? So what's that going to be? That's going to be 738.1 times 1.065 raised to the 15th power. And when I put all that in the calculator, the value that I get is 1898.3 billion dollars. All right, so that ends the lecture for section 1.1.